In this questions, there are a number of things for us to be thinking about that are important for us to employ in every type of problem. First thing is we're given temperatures. We're being given information about pressure. We have a volume, compression, and expansion, and we have a variety of units. So we want to not only visualize what's happening, but also make sure that we're not getting confused with the different units, which actually happened in this case because the textbook publisher published the incorrect answer in their own answer key was incorrect with this. So let's start with getting the temperature straightened out. I'm going to draw a cartoonish thermometer like so. And our equivalence point is 0.0 degrees Celsius, and that is equal to 273 Kelvin. Degrees Celsius, Kelvin. There's no degrees with Kelvin. We're told it's at 10 degrees Celsius, so 10.0 degrees Celsius would be 283.0 Kelvin. And it's, again, important for us to recognize there are 3 significant digits in the values that we're given. So that's going to be important in our final answer. So we have a tire that's inflated. Let me draw that tire like so. And then before that, we have air that was originally. So we have air that's outside this parcel of air at time 0 has a temperature of 283.0 Kelvin. So that's in its normal atmospheric pressure. Now we're not given units, but we can be simple with this and say it's 1.0 atmosphere. And we could even add more significant digits if we wanted. During the process, it's compressed to 28%. So for time 1, that occurs later, as the air is being pumped into the tire, we now have a temperature at time 1 and a pressure at time 1. And also, there are volumes involved in all of these. So we told the temperature, its original volume, and it increases to 40 degrees Celsius. So we get up to 40 degrees Celsius over here, and that is 313.0 Kelvin. So the new temperature at time 1 is 313.0 Kelvin. We know now that its air is compressed to 28%. So if we said that this has a volume of 1.0, then this now has a volume of 0.28, such that this volume is 28% of that original. So our original volume, we would say, is 1.00 units, whatever those units are, and the volume afterward, at time 1, is 0.280 units. And we're being asked then, what is the tire's air pressure afterwards? So we are looking for this P1. Now, one of the things for us to realize is that we are treating these gases as the gas involved as ideal gases. And an ideal gas means it follows the ideal gas law. And the ideal gas law is simply PV equals nRT. So we have P0 V0 equals nRT0. Now, N is the number of moles of the gas. So just like if we had 12 air molecules in here, that would be 1 dozen. We have some number of molecules that ends up corresponding to 1 mole of the gas. So what we know then, applying the law of conservation of mass, if we take these air molecules and pump them into the tire, that the number of molecules as well as the number of moles will be the same. So we know those will be the same. And we have the ideal gas constant. That is true for all conditions. So these two would be constant. So separating our variables from our constants, we end up with P0 V0 over T0 equals nR, which is a constant. So we know that the product of the pressure and the velocity, or the volume, divided by the temperature is going to remain a constant. That constant is equal to the number of moles times the gas constant. Applying this to our time later, we know then that P1 V1 equals nRT1, and therefore P1 V1 over T1 equals nR. And it's the same number of moles because of conservation of mass, and it's the same gas constant, so it is also equal to K. These two K's are equal, these two nR's are equal, and therefore, these are equal to each other. So we end up with a statement, and I'll move this up over here, that P0 V0 over T0 equals P1 V1 over T1. Now some of you may say, oh yes, we recognize that as the combined gas law. Yes, it is the combined gas law. But it comes from the ideal gas law. And that's why we can say, excuse me, and use this combined gas law, is because it comes from the combined gas, or the ideal gas law. So what we are looking for here is P1. So solving for P1, we get P0 V0 T1 all over V1 T0. It's going to equal P1. Subbing in our values for those, we have a pressure 0, which is 1.00 atmospheres. Our volume, which is 1.00 units. And our temperature, which is 200, our temperature 1, which is 313 Kelvin. Our volume afterward we know is 0.28, so we have 0.280 units. And our initial temperature was 283.0 Kelvin. Doing some dimensional analysis here, we see the kelvins cancel, the units cancel, leaving us with atmospheres. But what I want to draw your attention to here is that this 1.00 units divided by 0.280 units, it doesn't matter what the units are, whether it was liters or milliliters or cubic centimeters or cubic feet. Those units will cancel, and the ratio of those two volumes will stay the same irrespective of the units that are used. So then we put this into our calculator, and we find out that that pressure 1 is equal to 3.95 atmospheres. In fact, it's, if I include the other significant digits, 3.9500254 atmospheres to be exact. So then the question becomes, how many significant digits do we use? The primary data we're given comes with 3 significant digits. So in the end, we report only 3 significant digits. So P1 is 3.95 atmospheres. We're not asked to give the pressure in any particular unit, but we might as well express it in our common units. Both sets of common units, we use atmospheres and pascals, and the conversion for pascals to atmospheres is 1.01325 times 10 to the 5th pascals per atmosphere. So our atmospheres cancel, we're left with pascals. So we end up with P1 is 3.95 atmospheres. It is also equal to 4.00 times 10 to the 5th pascals. So when asked a question and it's ambiguous about the form of the answer, we can be a little more sophisticated and give it in multiple units. So that is part A. Part B, now we are told that it is driven at high speed. The tire is going to flex, the air and the volume is going to complex, so we might imagine that it's going to heat up. The temperature rises to 85 degrees Celsius, so we actually predicted that correctly. So we can now go to 85.0 degrees Celsius, which takes us to 358.0 Kelvin. So now counting for our numbers here, our data here, we have a little bit, we expect there's going to be some expansion. And what we realize is this is going to be up 2%, that volume. We're told that the interior volume increases by 2%. So our T2 is 358.0 Kelvin. Our P2 is what we are looking for. That's the unknown. And our V2, we are told, is 2% more. Now, it could be confusing. in this case? Are they referring to the 2% as in there was 100% initially, and it's 2% more, so it's now 102%? And so we have to read very carefully into that. The interior volume of the tire, and so that volume of the tire is 0.28, that is going to increase by 2%. So that volume is going to be 0.28 times 1.02 units. So again, we're looking for P2. Now, of course, it will come as no surprise that P2V2 is going to be nRT2. And solving for the constants, P2V2 over T2 will be nR. That will be a constant. Again, it will be the same constant for the other cases. So we could do this one of two ways. We could ask ourselves to, just to move from this one to this one, set these two equal to each other, or we could set the initial one to the final one. In general, it should make no difference. We should get the same answer. But my advice is to always use the first one because that's where our initial data is. If we have made any error in calculation from 1 to 2, we will also get the third answer wrong. But if we start with the first one and use that information, we're less likely to have an error. But hopefully we're doing it correctly the entire time, so you don't have to worry about that. So we then have P0 V0 over T0 equals P2 V2 over T2, again the combined glass law, and now we know why. Looking for P2, we end up with P2 P0 V0 T2 all over V2 T0. Those numbers then for initial pressure was 1.00 atmospheres. Our volume initially is 1.00 units. Our temperature at time 2 is 358 Kelvin. In our denominator, our volume goes to 0.28 times 1.02. And the initial temperature was 283.0 Kelvin. Doing our dimensional analysis, kelvins are gone, and the units were gone. I forgot to write the units there, and we're left with atmospheres again. The final answer is 4.43 atmospheres, 4.4293. And if we wanted in atmospheres and pascals, we can put in our conversion, 1.01325 times 10 to the 5th pascals per atmosphere. And that leaves us with a P2 equal to 4.43 atmospheres. And that is equal to 4.49 times 10 to the 5th pascals. Going back and checking our question to make sure we've done everything they're looking for. What is the new tire pressure in pascals? So where it was ambiguous for the first question, we're given it in the second question, we have overkill. Now I can tell you, and I won't take time to do that here, that it is true that if you use these numbers, set this equal, P1V1 over T1 equal to P2V2 over T2, you get exactly the same answers in both cases.